free. Welcome back, everyone. Today, we're diving deep, and I mean really deep, into one of the most fascinating and radical ideas in modern theoretical physics, the theory of entropicity, or ToE. Now, this isn't just another theory trying to staple everything together. It's a complete reimagining of what the universe is at its most fundamental level. For centuries, we've thought of entropy as a consequence, a side effect of physical processes. It's the reason your coffee gets cold, the reason your room gets messy. But what if that's backwards? What if entropy isn't a result, but the cause? The theory of entropicity proposes something truly mind-bending, that entropy is the foundation of everything. Space-time, matter, energy, even the bizarre rules of quantum mechanics, all of it emerges from entropy. So, let's explore this hidden architecture of reality, using a concept called entropic geometry. In classical physics, we learn that entropy is a measure of disorder. In information theory, it's a measure of uncertainty. In thermodynamics, it's the very arrow of time, the reason the past is different from the future. But ToE pushes us to ask a much deeper question. What if entropy isn't just a measurement? What if it's a field? A real physical field that permeates the entire universe, just like an electric or magnetic field. In this view, the universe isn't built from tiny particles or vibrating strings. Instead, it's constructed from entropic gradients, differences in informational curvature. Imagine a landscape. Where the land is steep, things roll downhill. In ToE, where entropy bends, spacetime bends. Where entropy fluctuates randomly, quantum behavior appears. And where entropy settles and stabilizes, the classical everyday reality we know emerges. This is the universe as an entropic landscape. ToE describes reality as something called an entropic manifold. Think of it like a vast, complex topographical map. Every single point in this map has a specific entropic value. Peaks on this map represent areas of high entropic curvature, where things are complex and information-rich. The valleys represent low curvature, where states are simpler. The ridges between them are the transitions, the boundaries between distinguishable states. And here, the kicker. What we experience as the flow of time is simply our movement through this manifold. Time doesn't flow on its own. It's not a dimension we travel along. Instead, it's a trajectory, a path we follow as the universe naturally evolves towards higher entropy. Time is a consequence of entropic change. One of the most powerful and intriguing ideas at the heart of ToE is something called the ln2 threshold. That's the natural logarithm of 2, a constant that mysteriously pops up everywhere in science. You find it in information theory, in thermodynamics, in statistical mechanics, and in quantum information. It seems to be a fundamental number of the universe. ToE gives it a profound new meaning. It proposes that lane 2 represents the absolute minimum entropic curvature difference required for any two states to be physically distinguishable. Think of it as the universe's smallest pixel. If the difference between two states is less than ln2, they blur together into a single, indistinguishable reality. If the difference is greater than ln2, they become separate, distinct, and physically meaningful. This critical value has a name, the OBD curvature invariant. So, it's a universal constant that draws the line between what is potential and what is real. It's the smallest possible step the universe can take. Now, if distinguishability requires a finite entropic difference, a finite step, then something incredible follows. No physical event can happen instantaneously. Every single transition, every measurement, every interaction, every quantum jump must traverse a finite entropic distance. This is called the Norrish principle, and suddenly, so many puzzles start to make sense. It explains why a quantum collapse, while incredibly fast, isn't truly instantaneous. It explains why there are fundamental limits to how fast information can be transferred, like the speed of light. It explains why it takes time for classical outcomes to emerge from the quantum fog. Even the expansion of the universe itself has an entropic pacing. The universe doesn't rush because it simply can't. It must obey the fundamental entropic geometry that lies beneath it. Let's talk about quantum mechanics, that beautiful, bizarre realm of superposition, uncertainty, and entanglement. ToE reframes all of these mysteries, not as strange exceptions to the rules, but as natural, logical consequences of entropic geometry. What is a quantum superposition? where a particle exists in multiple states at once. In ToE, it's simply a region of the entropic manifold where the curvature is too shallow to enforce distinguishability. The landscape is so flat that different states can't be told apart. 2. And what about the collapse of the wave function, where a particle snaps into a single state when measured? That's what happens when an interaction forces the system to cross that critical ln2 threshold. The landscape suddenly becomes steep enough to create a distinct, measurable reality. Even spooky action at a distance, or entanglement, finds a home here. Two entangled particles aren't communicating faster than light. Instead, they represent two regions of the entropic manifold that share the same curvature. They are linked not by a mysterious signal, but by a shared underlying geometry. What happens to one instantly affects the other, because, geometrically, they are connected. All the weirdness of the quantum world becomes the predictable logic of an entropic universe. In the theory of entropicity, spacetime itself is not fundamental. It's an emergent property, a shadow cast by the deeper reality of the entropic manifold. Where entropy curves, we perceive gravity. Where entropy flows, we experience time. Where entropy stabilizes into persistent patterns, we perceive matter. Matter itself becomes an entropic excitation, a stable, self-perpetuating knot in the fabric of the entropic field. This single elegant perspective unifies so much of physics. Gravity becomes the geometry of entropic curvature, just as Einstein described it for spacetime. Inertia, the resistance to change in motion, becomes resistance to entropic displacement. And mass, the amount of stuff in an object, becomes a measure of its entropic density. The entire universe, from the smallest quantum fluctuation to the largest galactic supercluster, becomes a single, coherent entropic structure. If entropy is truly fundamental, then so many of our longest-standing scientific puzzles begin to align and find their place. The one-way direction of the arrow of time, the discrete, quantized nature of energy and quantum states, the emergence of our solid, classical reality from the probabilistic quantum world, the geometry of space-time and gravity, the ultimate limits on information transfer, even the structure of physical law itself. The theory of entropicity doesn't seek to throw away the last 100 years of physics. It reframes it. It suggests that the incredible diversity of physical phenomena we observe might all arise from one single, underlying principle, the geometry of entropy. This theory invites us to rethink the universe from the ground up, not as a collection of particles, waves, or even fields in the traditional sense, but as a dynamic, evolving entropic manifold, a universe where distinguishability, curvature, information, and time all emerge from the same hidden architecture. It presents a reality where the answer to what is everything made of isn't a thing, but a principle. Thank you so much for joining me on this journey into one of the most exciting new frontiers of thought. This blew your mind. Make sure to like, subscribe, and hit that bell so you don't miss our next exploration into the mysteries of the cosmos. Welcome to a new way of seeing reality.